Okay, let's start the last session of the morning. It's my pleasure to introduce Vincent Jugé, who works at Université Gustave Eiffel near Paris, near Euro Disney, I think also. Yeah. Vincent Jugé got his PhD in 2016.
Yes.
Yes. At Cachan.
Non, Paris 7.
No.
Université Paris-Cité.
Okay, Paris-Cité, sorry. He got his studied in École Polytechnique.
Yep.
And then I think so. He's interested in many topics like braids, for example, from algorithmic, theoretical, and algebraic point of view, but also today an algorithmic topic about efficient top-down updates in AVL trees.
Okay. Well, thank you very much for the gentle introduction. Thank you very much to the organizers. I'm very happy to be here, and I'm super excited. Like, I could sleep a few hours tonight. And so, as you can all read, I will mention stuff about efficient top-down updates in AVL3. So actually, in the past few years, I had more been working on subjects like sorting and so on. So it's in the same vein, but not exactly. But I was afraid it might be too intersected with Sebastian's talk before I saw it. So I decided to speak to you about something that I started working on last year. So it was just by an accident. I like to do Olympiads in mathematics or computer science with students like in bachelor or high school. And I was too lazy to write an appropriate data structure. So I decided to start from scratch again. Okay, I mean, it was more fun than having to find a library and to download some articles on Sci-Hub. Okay, and eventually I thought that, oh, some idea needs to work. So certainly somebody has found it already. And well, it turns out that sometimes yes and sometimes no, as we will see in the talk. Okay. So first I will present to you what we expect from balanced binary search trees, like what is the goal of what we will do during the presentation. Then we'll balance AVL trees efficiently bottom up, and afterwards top down, which is a bit harder. And finally, we'll conclude. So it's at the end with the conclusion. So first, well, we want to maintain ordered sets of elements. And so I'm wondering which kind of data structure I should use to do that. So basically, there will be a bunch of queries I need to answer in an efficient manner. And my basic query is like, I have some key K, I have my set S, and I want to know whether the key K does belong to the set S or not. So if I just want to answer this kind of queries, well, a plain old sorted array plus a dichotomy approach should be fine. Okay. So for instance, I have this 7th element array, okay, in blue-gray area. So this is the span of the array, which is likely to contain the element 3 if the element 3 is present. So it's just a full array so far. And then what I will do is that, okay, I will look at the median value. Here it's 7, 3 is smaller than 7, so definitely I can discard the right part of the array and just focus on the still shaded part, which is on the left. I continue, and oops. Well, the answer was no. So of course, it's not what we did. We just passed the array sequentially from left to right, and so there was no 3. But if I were a computer, I would have done this. And so now imagine we have a second kind of queries, which is I want to insert a key K in my set. Okay. So here it's written add 3, it's an order and not add 6. Okay. So what I have to do here is basically, okay, I can add 3 and find the location where I had to add 3 is easy. But then I just have to, well, to shift right every other element. And this is super long as a process. Okay. So it will definitely be most inefficient. Okay. And so I need to find another data structure. So what I will do, I mean, what you would do, of course, is that you would just use some whatever binary search tree instead, where basically when I'm on the left, I'm smaller. When I'm on the right, I'm larger. And in particular here, I mean, the route I chose. So from my initial, I mean, set before adding the 3, it was just the place where I started my dichotomy, etc. And so now if I want to add 3, well, I just say, oh, I should go left of 7, and then right of 2, and then left of 4. And so I get a 3 here. Okay, no big deal so far. And finally, if I want to delete a key k from my set, okay, well, if I want to delete a leaf, well, I just delete it. And if I want to delete an internal node, okay, well, there are some tricks to, finally delete a leaf anyway. So for instance, if I wanted, to delete the element 7, which was present in the root, okay, it was at the root. What I would do is that, okay, I want to delete 7, but now I have to replace it by something else. So I would either take the label just above or just below. In my case, okay, I just randomly just below. And then this one, I have to replace it by something else again, because it's not yet a leaf, but it's close to a leaf. Okay. And so, okay, I replace it by the leaf with label 3. So it gives me this. Okay. So basically, inserting a key, it will of course result in inserting a leaf in my tree. And deleting a key, well, I might want to delete a non-leaf at all, but I will end up deleting some leaf and making some element moves in the tree itself. Okay. So just the kind of questions we will be focusing on. So now, well, okay, yeah, I have my balanced, my binary search tree, but I want it to be balanced, or at least I want it to be of small height. Okay. So the smallest kind of height you can have will be logarithmic in the number of elements. Okay, so let's look for that. And a standard way to ensure that my tree will be of a logarithmic height, even in the worst case, is to maintain some kind of rank and balance between the ranks. So here I will present 4 families of trees with these kinds of ranks and balances between the ranks, just to give you an illustration. So the first family I want to talk about is weight-bounded trees. So the rank of a node, so X, okay, it will just be the size of the subtree rooted at that node plus 1. So the plus 1 is just like, it makes things easier when you have to compute stuff, okay? And you can imagine just the number of null nodes that will be hanging below my node here. So in sense, here I have 1 null node, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. Okay, maybe there is a typo, or maybe I can't count. I'm a computer scientist, I can count up to 2. Okay. Anyway, so my notation in general is that I have a node X. The left side will be X1, the right side will be X2, and just below a node, I will write the rank of the node. Okay. So here, basically, by definition of what I expect from the ranks of the node, the rank of a node will be just the sum of the rank of its children. That's why we are happy to have the plus 1. Okay. And the rank of a node is just a 1. Okay. And now, so this is the definition of the rank, and the definition of the balance I want to enforce to make sure that my tree will have logarithmic height. It will be that the rank of any child of node X must not be too large compared to the rank of X itself. So let's say it must be at most alpha times the rank of X. And we have good algorithms when alpha is a real parameter between 1 over square root of 2 and 9/11. We could have it also for alpha larger than this, but it results in less efficient algorithms and less efficient trees, so we'll not bother. Okay. So this is one family of trees that was invented like 50 years ago. Okay. And actually, this criterion, it's just about the shape of the tree, but not on the content of the nodes of the tree, okay, on the labels. And therefore, it will be the case in all the trees I'm looking at. So I just forget about the labels of the nodes in the tree. Okay, just gives me smaller pictures in the slides. And then I have AVL trees, which will be the trees that we are focusing on in this presentation. And while the criterion here is different, so the rank of a node is just its height. Okay, so in particular, the rank of a node is just the maximum of the height of its children plus 1, and the height of a null node is -1. And now the condition that we want to enforce to make my tree an AVL tree is just that my height should be at most, should never be larger than the height of any of my children plus 2. So basically, the difference between the heights of a node and its children should be either 1, in case we say that the child is a 1 child, or 2, and then we say that the child is a 2 child. So the blah child is just when you have a difference of heights that is blah between the parent and the child. Okay. So for instance, here, I wrote the height of the different nodes I had in my tree. Okay. By the way, this is the most complicated formula that you will find in this presentation, okay, which is typical for what I have seen during this week. Okay. A third family, which I did not know about until like last summer, is weak AVL trees. Okay, well, they also have a bunch of other names, but I will stick to this one because it has AVL trees in it. And there, I mean, there is no intrinsic notion of what the rank of a node should be. So in particular, it's not uniquely defined by the shape of the tree. Rather, we only ask that the rank of a null node should be -1, and the rank of every node should be a 1 or 2 child. So actually, in the official definition, you have other criteria, but I will just omit them because they will be useless for what I'm saying here. So I'm slightly lying, but just for the sake of simplification. So for instance, here, I have a family of ranks I could have assigned to my nodes. So here, I mean, this node, it has 2 null nodes as children, and so its rank is 0, it's okay, because like 0 is -1 + 1. This one, it's allowed to have rank 0 or 1, for instance. This one, it may have rank 2, this one may be 4, etc. So whenever you take some node and its children, the difference between the ranks is 1 or 2. This is fine. This is a weak AVL tree. Well, you could, oops. Yeah, so here you see I have the same tree, but with different ranks, okay? It's still a weak AVL tree, so what I was saying that the ranks are not uniquely defined by the shape, but it's okay. I mean, just gives you 2 different rank assignations to the nodes for the same tree. Whichever you find, whichever you happen to be on, is fine. A fourth family, which is the last one that will fit on this slide for obvious geometry reasons, is red-black trees. And in fact, they turn out to be in a very good bijection with weak AVL trees, meaning that you will paint a node. Can you see the colors properly? I'm colorblind, but this looks like strange. It looks very nice on the computer and not so nice on the screen. Yeah, wow. So this is red and this is black. Okay. Oh, wow. As soon as it's not the same color, this is fine. Okay. And so here, I just decided to paint red a node when the rank of the node was even and the rank of its parent was odd. Okay. Well, you can say it in different ways, like with integral parts of blah divided by 2, but it's the same definition. Okay. And so here, it gives me red-black trees, and the standard definition of red-black trees would be that basically from any node, when you go downwards to the leaves, all the paths, they will have the same number of black nodes on them. Okay. And then you can see that both definitions coincide. And so in particular, I mean, a weak AVL tree is a red-black tree and vice versa. And any coloring actually gives you the rank assignation you wanted to have and conversely. So that's why you have a good bijection between the two families of trees. This is that they don't come with the exact same families of algorithms because you don't store the same information about the ranks of the nodes. Okay. So in one case, you will just remember the difference between the ranks of the nodes, and in the other case, you will just remember the color. So I mean, you have lost or gained a little bit of information in each case. Okay, so in particular, I will be mentioning a lot things about weak AVL trees because they were invented like 10, 15 years ago. So 15 years ago, if you take the conference version, and 10 years ago, if you take the journal version, okay, to solve problems that were not solved about AVL trees. And we'll solve this problem about AVL trees by using the same recipe as those inventors of weak AVL trees used. Okay. So in a nutshell, here are these 4 families of trees. Okay. And so, for instance, I mean, like AVL trees are somewhat, I mean, they are the older family. Okay. So maybe they were easier to find. Okay. And also they have the best height constraints on the trees that are in the family. Okay. So somehow we might think, oh, maybe they are better. But at the same time, I mean, now, I mean, if you look at the number of amortized write operations per update, or whether there exist top-down updating algorithms, the answer is crappy compared to what is true for the 3 other families of trees. So I'm going to explain in the next slide what is amortized number of write operations per query, and why we are interested in top-down algorithms. Okay. So basically, here you have some stuff that looks dark. Okay, so you want to get rid of it and make it fair like everybody else. Okay. So, well, first we are looking at write operations. So why? Well, it's just that typically writing some stuff, it takes much more energy and time than reading it. So for instance, it took me slightly more than 1 hour to write the slides I'm presenting to you now. Okay, and certainly I remember some kind of subliminal slides that we had 2 seconds to read, and I mean, like, I can't type as fast as that. Okay, so in general, also, I mean, like in a distributed context, for instance, if I make some write update, then I need to let everybody be aware that I wrote something, and this is super expensive. Okay. While reading is just that, okay, I load some stuff, it's in my cache of my computer, and then I can read it again, but like it's less expensive. Okay. Second, so now what is amortized complexity? Well, basically, you can just say that you will take arbitrary sequences of operations, and you will take so finite sequences, okay, and then you will take the average complexity about on this sequence of operation, and then you take the worst case possible average complexity. Okay. So, for instance, if we look at weak AVL trees and you look at the article of the authors, okay, basically, if you have Q queries starting from an empty tree, you would have at most 13 Q updates that corresponding to, I mean, reevaluating the rank of a node or making pointers changes, because like I had 2 children and now I will have 2 new children. Okay. And so in particular, the amortized write complexity will be at most 13 operations per update. Okay. So this is typically important when you are not concerned with the cost of a single update, which could be high, but the overall cost of building your entire set with your favorite data structure. And finally, what is it about being bottom-up or top-down? So here, imagine I have this tree, okay, and I want to insert 2 and then later 8 with a bottom-up algorithm, okay. So, well, I compare 2 to 4. I see that it's on the left because it's smaller. Then I must go down and see that, oh, it should be on the right of 1. So I will pause number 3. And then now I create my new leaf. I have stored the ranks, that is allegedly what I would like to be the height of the node. Okay. And then, well, now I have a problem because the height of 3, I mean, is obviously incorrect. This one is incorrect too, but it's less obvious because you cannot see it from a local point of view. But the height of 3 is definitely mostly incorrect, and it's easy to check. Okay, so now you make it correct, and then you continue. Now you realize that the height of 1 is incorrect, so make it correct, and then you see that the height of 4 is incorrect, so you make it correct. So you had to go all the way down, and then your write operations, they were bottom up from the leaf to the root, and now you can start inserting 8. Okay. So in particular, you have to wait until the end before you can start inserting 8, because maybe you would have some local changes around the vicinity of the root, and they may have some impact on what you have to do when you want to insert the 8 value. Okay. And then, okay, I do the same thing. No surprise here. I'm fine. Why? So here I will present to you an idealistic version of what a top-down algorithm would do. Okay, I'm a bit lying, but it's okay. And so if I want to insert 2 and 8 in a top-down manner, it means that I would just have processes that will do one pass from the root to the leaf, and that's it. So we'll be done. And so in particular, okay, let's say for the sake of the argument that I just need to look at one node and it's and I can guess what the new height should be, etc. Well, I try to insert 2, so I realize that, oh no, my new height, it will be 3, okay, for magical reasons. Okay. And I need to go left to continue inserting 2. And now, since I only need to look at, I mean, local things, I can try inserting 2 on the left side and 8 on the right side simultaneously. Okay. So in particular, whenever I'm doing something in parallel, okay, it's much more efficient because otherwise I would need to wait for a super long time to make sure that I can start my new query, while now I can just do them in parallel. Okay. And then I can continue, and this is much faster. So in general, I mean, like if you have, even in the absence of having several processes at the same time, if you have a top-down algorithm, it's quite faster than having a bottom-up one. Okay. So we would like to have this kind of property too, because everybody else has it. And even if I didn't understand the impact of it, like if everybody wants something, then certainly it must be important, and therefore I should do it as well. I'm like, okay, I mean, it's a safe bet. So now we'll try to rebalance AVL trees bottom up in an efficient manner. So updating AVL trees, I mean, it's all about eliminating anomalies in the node ranks. As we saw before, like my new height was incorrect. I had to, well, to correct it again. So for instance here, I mean, like one kind of anomaly I can have is what we saw before. It is what I call a zero edge, because I mean, here I have a zero child somehow. Okay, like the difference between my rank and that of my parent is zero. So in general, I will represent zero edges like this. So I have the rank of the node just below the node itself, and I put in bold red the edge that is problematic. Okay. And I don't really care what the rank of my sibling would be. So here, what we can do is that actually we will just increase the ranks of the nodes. End of story. Okay. Another case that can happen is actually, so now here I have this tree, and then, oh, I had to delete the three I just added. Okay. So now I have a problem because here I have a leaf with rank 1, but its actual rank should be 0 and not 1. So I need to update it. Okay. And so in particular, if I don't forget to write null nodes, I can see that, I mean, both my children here are 2 children, and this is a problem. Okay. So in general, I find it, I call it 4 nodes, because it's a node where when you look at the differences between the rank of the node and its children, so sum of the differences is 4. And this should never be the case. Okay. And these are the 2 kind of anomalies that we can have. Okay, we could have 5 nodes or maybe -1 edges, but it turns out that this never happens. So now we'll see how the algorithm, the plain textbook algorithm from 60 years ago, works about eliminating these 0 edges and these 4 nodes. Okay, and later we will adapt this algorithm. So here, I imagine I have some node with rank R, and well, my child, let's say my left child, for the sake of symmetry, also has rank R. So here I have a 0 edge. Okay, and I want to get rid of this 0 edge. But maybe, for instance, my other child has rank R -2, and my grandchildren here, they have rank R -1, both of them. Okay. Well, what I should do is to reorganize my tree, but it must remain a binary search tree. So the left to right ordering is important. And the structure of the tree, well, shall change, because otherwise I will have a problem. Or at least the rank assignations should definitely change. So here, oops. Yeah, okay. So I cannot just say that here I will have a rank R+1, because there I would have a 3 child. So I need to do something else. It's called a single rotation. Okay. And basically here, so if I take the, so this is supposed to be blue and this is supposed to be a gray. Okay. But like the blue part, it's exactly the fragment of the tree I was considering there. And then maybe there are subtrees attached to this node, and that node, and they will travel along with their root. So I will just modify, I mean, like, who are the parents of this node, and maybe these 2. Okay. And so in particular, for instance, here, so I have an example where I have this kind of rank assignations with R = 2. Okay. And okay, I decide that now the new parent of both these nodes, I mean, they should have a common parent, so basically this one. And then there is just one way to make all these nodes coalesce into one tree. Okay. And then I can recompute the ranks, because like my rank shall be the maximum of the ranks of my children +1. So we have this kind of rebalancing operations. And now I don't have a problem anymore. Maybe I have a problem above, okay, because I changed my rank. So maybe this created a 0 edge. But for now, I'm fine. Okay. This will be a problem for later. As my students tell me, you shouldn't do tomorrow what you can do the day after tomorrow. Okay. Well, then you have other cases. So this one, where actually my, middle grandchild had rank R -2 instead of R -1. I do the same exact rotation, but now, the resulting tree has a root with rank R. So in that case, I'm very happy, because actually there will be no more 0 edge. Okay, like there was no 0 edge above myself before. There is still no 0 edge above my new self. Fine. A third case is possible. Okay, it's when this node has one two child and one right child, but one child in the middle. Okay. Then I need to split it further. It works okay. And a final case is when I have a zero edge and the other sibling has a rank R-1. Okay. And in that case, again, I might have propagated my zero edge upward. So in general, we can classify all these four operations into three classes. So we have this one, we say that is transient because it can just propagate the zero edge. These two classes are terminal because once I have done them, then I have no zero edge anymore. And this one, we call it spurious because it can never happen in practice. Okay. So just that if you do the induction, I mean, like whenever you find a zero edge, it's just because you created it at the bottom, at the leaf, or because you had previously a transient operation. Okay. But all transient operations, I mean, they result in having a node with a two child. Okay. Even if this one was not spurious, it would have a two child. Okay. And therefore, the node at the bottom of the zero edge, it must have a two child, and this is not possible here. Okay. So it's just, I mean, we can deal without noticing that this case is spurious, but it just saves us computational time when computational effort is important. Well, finally, like with deletions, when you are dealing with 4 nodes, which may happen during deletions of elements, well, you can have a similar classification. It really looks like before, just have a, well, basically these are the same kind of operations. And here you have no spurious case, just one terminal one and 3 transient cases. Okay. So far, so good. I mean, at least it gives you some algorithm that works rather well in practice. Okay. And so I wanted to know, like, is this efficient, or what makes it not so efficient? Because like I had my theta of log n in the amortized worst case complexity. Okay. So let's look at an evil pair of people who can make things really, really, really go bad. Okay. So one of them will be a super rich billionaire. The other one is this friend called Donald. Okay. And so they make seemingly innocent operations. Okay. But imagine I am looking at some branch of a large tree, and I want to insert a node just there. So then basically what I will do, I will just apply the Scrooge-McDuck operation and increase every node's rank by 1. And then I say, oh, crap, my mistake. I should not have added this node. And so now I call Donald, and I downgrade each node's rank again on that branch, but I can do it forever and ever. And each time I do it, it makes log n operations, okay, because just my branch is log n long. Okay. So definitely, I mean, like I have a simple example where I will not do pointer moves, okay? I just do rank reassignations, but I do a logarithmic number of them for each query. So definitely, this is not amortized constant. So what we wouldn't want to do that is to defeat this evil pair. So when we want to defeat some very powerful team, well, you need to put an even stronger team, okay, in general, okay? Or you can call a very powerful triplet. So in our case, we will call these 3, well, nice-looking ducks. We'll call them Bernard Hauptler, Siddhartha Sen, and Bob Targent. So Robert Targent for Philippe, okay? And well, I mean, it's well known that these 3 ducks, they have a super book that contains all the truths about the universe, okay? So I found the French cover much nicer than the English one, okay? And so it's called Le Manuel des Castors Junior. Okay. And in this book, if you open it, okay, at some point you find that there is some extracts from ACM transaction on the algorithms from 2015, where they have written the article on rank balanced trees, which are weak AVL trees. Okay. And in there, they have a lot of ingredients that you can use actually to solve this problem of inefficiency in AVL trees. Okay. So let's look what we can do. But first, I mean, we definitely need some way to stop propagating errors faster. Because if we don't do it, we already have a counterexample that will force our complexity to be bad. Okay. And so we will do it by demoting and promoting nodes. I will show you what this means on some examples somehow. So for instance, you have some nodes, we will call them hollow, and they can be demoted. So we say that the node is hollow when it has a 2 child, and all its descendants with rank at least R-2, they have a 2 child. So basically, I mean, my 2 child could be on the left or on the right, okay? And the 2 child of my 1 child could be on each left or on each right, so I have several choices. I don't really care. All these nodes are hollow nodes. Okay, and it turns out that, so here is an example. You have a few more of them, but the strategy works in the same way for all of them. What you can do is that, okay, maybe I can look at the descendants of those nodes of rank R-3 here. Okay, gives me 2 more nodes. And I don't know if this node's rank is R-4 or R-5, but it won't really matter for what I do. Okay. And then I just try to rearrange the parentship relationships between these 7 nodes, okay, which will remain in the same left-to-right order, and the 5 nodes that are supposed to be their ancestors. So I can rearrange them so that here I had rank R, and now I have rank R-1, and I'm still having an AVL tree. Okay. So this works in all cases. So in particular, that's what I call demoting. It's I had a tree whose root had rank R, and now I get another tree whose root has rank R-1, so it's a bit smaller. Okay. So in particular, if I'm propagating a zero edge, so by increasing the rank of the top node of the zero edge, and the resulting node is hollow, then what I could do to stop propagating the zero edge is just to demote it. And then it will be final, it will be a terminal operation, and I like it. Okay, so I try to find the simplest way to stop propagations that could not be stopped by the original algorithm. And then you can try doing something similar when you are doing deletions of elements. Okay, so here, actually, I have some family of nodes that can be promoted. So I call them full nodes. So a node is full when its only children are 1 children. And actually, its only grandchildren are 1 children too. And one of these or that node, so those on the middle, they must also have 1 children only. So the trick does not work if this one has 1 children only. Okay, it really needs to be in the middle. And in that case, so I have 2 symmetric cases here. So there is no bargaining or whatever. In this case, for instance, I take these 5 nodes, okay, and I just reassign their parents. So I restructure a little bit the tree. And now it gives me a new tree with rank R+1. Okay. And so in particular, when I'm propagating a 4 node, okay, if I had a transient operation, it would mean that the resulting AVL tree, it would have a rank R-1. But if the root I get here is full, then I can just promote it again. Okay. And then it will be a terminal operation. I'm just doing that. And it will be enough, actually. So, I mean, when looking at this new, I mean, a bit enhanced procedure, what we can observe is that, well, when you have a deletion operation, okay, so a transient operation that occurs during deletion, so for getting rid of 4 nodes, okay, it will create no full node, because if it created 1, then I would promote it. And it destroys 1 2 child. So the number of 2 children in total, it will be decreasing. And if I took some insertion operation, so some transient operation during insertions, it's just the one where I promote, I change the rank of the node, okay? Well, it will destroy 1 full node, okay? And it will create 1 2 child. So you just have to do some case analysis. It's not trivial, but it's easy. Like a first-year student has the mathematical tools to do it, and some do have the wit to do it, but okay. And now, from these 2 observations, we can prove that if you start from the empty AVL tree and you perform Q queries, then you will have a linear number in Q of right operations. And the proof is exactly following the same pattern as what was used for weak AVL trees. You just have some tree potential. So in our case, the tree potential, the potential of a tree is just twice the number of full nodes plus once the number of 2 children. Okay. And if you look at it, I mean, each transient operation that you had here or here, it decreased the tree potential. So what happens in the end is that if I have Q queries, okay, I may have Q terminal operations, I mean 1 per query, plus a certain number of transient operations. I don't know when they will happen, but if I have T of them, the tree potential in total, it will increase by a linear term in Q minus T, or maybe it will increase less than that. Okay. But it must remain non-negative because I'm just counting a number of nodes in the tree. Okay. And therefore, T, it must be linear in Q. So overall, okay, now I have my amortized complex, constant complexity in numbers of write operations for AVL trees, okay, which, well, I mean, people may have looked at it for quite a long time because they invented other data structures that had this property. So if they could have proved it on AVL trees directly, they would have done it. Okay, so this is nice so far, but not nice enough to get my paper accepted. So maybe you can do something else and try also to have an efficient top-down algorithm. Well, actually, it started the other way around. I got the top-down algorithm first. It was just a disjunction between like 8,000 cases, and the paper contained a link toward like a text document with the 8,000 cases, and a program for verifying that the document was valid, and an explanation why the program was for verifying was correct. And okay, this one was not accepted, but it's a good idea that it was rejected. Okay. Well, I mean, the result was correct. As a proof, nobody wants to read it, and actually, nobody should. Okay. At least not the 8,000 cases paper. Okay, so here we will continue borrowing ideas from weak AVL trees. Okay, and they use the notion of safe nodes, which was invented a while before, like I think in the 70s. Okay, I mean, it's the citations they make, and so I will explain to you what a safe node may be in our context. So here, I mean, we'll say that a node is insertion safe if it can stop propagating 0 edges. And then I will have something deletion safe for stopping propagating 4 nodes. Okay. So here, I took this, this small tree. It doesn't look small, but it's the smallest that has some properties that we will see at the end of the slide. Okay, it's like in 18 overlays. So imagine I want to insert some leaf here. Okay. And now if I try to apply even my enhanced insertion algorithm, okay, I just need to increase the rank of this node. Then I have propagated my 0 edge. I continue up. So now here I have a node of rank 5, but here I recognize that this node is hollow by looking at this fragment of my tree. And so, okay, I can, it's hollow, so actually my operation was terminal. I don't want to show you the resulting tree. It would be a nightmare to code in TXZ. Okay? But the operation is terminal. And so this node, okay, it would stop propagating 0 edges that were coming from inserting this leaf. Okay. And it turns out, so in general, if I wanted to insert some leaf here, this node was unsafe, this one was unsafe, this one was unsafe, this one was unsafe, this one was safe. The others that are above, I don't care. I will not look at them. And so in general, we have a nice characterizations of insertion safe nodes, which are nodes that are not full. Okay. Or maybe they can just have a small rank and then you have an ad hoc criterion. So here, for instance, for each node, I indicated whether they were unsafe or safe. Okay. And so it's a local criterion, so it's super easy to detect in live. Then you also have a local criterion for being deletion safe. So deletion safe means that we will stop propagating 4 nodes in a similar manner. Okay, so it just depends on a finite neighborhood, okay, which is maybe nasty. But it depends on which branch contains the leaves that you want to delete. So for instance, I mean, on the same tree I presented to you, if I want to delete this leaf, all my nodes here will be unsafe. Okay, well, I ran my computer just to make sure I was not saying bullshit. But if I want to delete this leaf, then this node magically becomes safe. So really, it's not intrinsic to the node, it's intrinsic to the node and which branch I'm working at. So it's a bit more complicated, but it's standard when you are working with balanced trees, that deletions are quite significantly harder to deal with than insertions. Okay. Anyway, I have some finite neighborhood I should look at, and I know from this neighborhood where is the branch I must act on. So I will know whether my node is safe or unsafe. So now here's how we can use safe and unsafe nodes. So for insertions, let's say, it would be the same kind of strategy in both cases. Well, I want to insert my node along this branch. And imagine I find a safe node. Well, I'm super happy in that case, because I just need to insert my node below this safe node. And even if there are some propagations of zero edges, so of errors, it will never go above this safe node. So if you find a safe node, you can just recursively decide, okay, I will insert my new leaf below the safe node, and that's it. So in practice, if I took like some random AVL tree, okay, I did not do it, but I would expect that quite a few nodes would be safe, and I would just need to go down my branch, and I would find some low-level safe node, and it would be the final safe node, but it would be so low level that, okay, it will be very efficient in practice. I mean, that's what my node suggests should happen on average. I have absolutely no proof. It's just that, okay, sounds reasonable. Okay, but so if I succeed quickly at finding such a node, so basically it was not too far away from my root, then I just restart and insert my leaf below this node, and my write cost was 0 in that case. However, if I was unlucky, then I need to do something because I mean, like maybe there is no safe node at all. I don't know. Okay, and I want to have a top-down algorithm. So top-down algorithm, it's a bit less idealistic than what I presented to you before. I may have a lookup. Okay, it means that I'm allowed to look at like D levels below me. Okay, and in particular, when I have several processes at a time, they manage to never look at the same area because it might change. Okay. But it's a detail. And so imagine now, okay, I have a really, really large bunch of consecutive unsafe nodes. Okay. So now, I mean, I will take the dth of these nodes for some parameter d that I will choose later on. And I decide that, okay, I will make this node safe. How can I do that? Well, actually, well, if I can do it, so I would like to promote it and to make it safe at the same time. So if I can do it, then now it will have a rank R+1 and be safe. And but now, of course, I have an error, but I will propagate this error up to the top because all my nodes here they are unsafe. Okay. So in particular, so I propagate my zero edge. Okay. But I mean, doing this is okay because my node it was unsafe, which means that it was full, and therefore I could promote it. And the resulting node from the promotion, it would definitely not be full, so it would be safe. So it works rather well, and in particular, well, so the write cost of this batch operation, it will be linear in D, let's say, maybe a +1, and the variation in potential of the tree, well, whenever I had to transmit the zero edge, okay, it would let my potential decrease, and just this promotion, it would let the potential increase by constant. Okay. So in general, the potential as a result of this batch operation, okay, it increased by at most a constant minus d. So if d is super large, it means that my potential it will decrease in the end, and this is good for me, okay, because I want to use the same kind of analysis that I use for the bottom-up case. And then, well, for deletion, it's the same story. It's just that instead of promoting a node to make it safe and then propagating a zero edge, you want to demote a node and make it safe and then propagate a 4 node. Okay. But basically, it's the same idea. Okay. The trick is that it's quite substantially harder to do this step of demoting a deletion unsafe node and make it safe at the same time. Okay. And so a bad correct answer to this question, to this challenge, is that when you have 4 unsafe nodes in a row, you can do it. Okay. So it's just, I mean, like, you don't want to do it, but you can. So the good answer is like you have just 12 cases you look at. They are all simple, but it doesn't fit on one slide, and nobody wants to hear it during an oral presentation. Okay. So you should not do that, but you should know that you can do it. Okay. And so basically, so this was exactly what was done for weak AVL trees in general, but the base bricks were not the same. Okay. So finally, I'm like, if I start from an empty AVL tree and I have Q top-down queries with this algorithm, then it will trigger a linear number in Q of write operations. And it's basically the proof that I already mentioned, I mean, before and just 2 seconds ago. So whenever you have a batch of D transient operation, if D is large enough, then it will decrease the tree potential, but it's just D operations, D seminal write operations, this batch. Okay. And so now if I have Q queries and B batches, well, I mean, like the number of batches will be linear in Q because of the same arguments as before. And therefore, the total number of write operations will be linear in Q as well, okay? Which is what exactly we wanted. We wanted to have a top-down algorithm with a constant amortized write number of operations per query. So finally, well, this was a story. Maybe we want to remember something from it. Well, I mean, the obvious answer is that AVL trees, like other data structures, they have efficient bottom-up updating algorithms, and they also have efficient top-down updating algorithms. So by the way, I want to thank once more the authors of the weak AVL paper, because at some point they explicitly say, we think there is no top-down algorithm for AVL trees. So I mean, this is a good idea to have conjectures. I mean, that can either be true or false. And even if the conjecture is false, it's even a better bait because people will be so happy to disprove you. Okay. So whenever you have a conjecture on something and you want people to be attracted by what you say, conjecture the opposite of what you think. And then people will be super happy to say, oh, by the way, he was wrong. But they really want to work on it. Okay. Well, I mean, proving something that everybody expects, yeah, okay, it has less value. Well, then, of course, there are ongoing tasks. So for instance, we might wish to improve D. So right now, D is equal to 20. The first version, it was like 58. So I mean, it's an improvement. If I resubmit the paper 3 times and divide the D by 3 each time, it would be like less than 1. It would be good. Okay. So for weak AVL trees, it may be something like 2. So, okay. I mean, well, I mean, if you let the D and 0 commute, it's the same number, but otherwise it's larger. Okay. And then we would also like to delete internal nodes in an efficient top-down manner. So for instance, we could delete internal nodes with a top-down algorithm as well, using this kind of rotations. But if you just use this kind of rotations, I mean, it's impossible to have a constant amortized number of write operations per query. Okay, I mean, like, you need to know what you want. Okay. And then, well, there are also some stuff from the paper about weak AVL trees that were not looked at for AVL trees. For instance, they have what is called a rank-based analysis. So basically, I mean, if you do write operations around the leaves of the tree, yeah, okay, these are write operations, but who cares? Because, I mean, if you have several processes, I mean, it's unlikely, if they are random, that they will go at the same leaf of the tree. However, if you need to always rewrite things at the root of the tree, then it will be very costly because everybody will need to be aware that there was some change. Okay. And so, I mean, like, what we would like to prove, and certainly it must be true because it's the same structure of a proof, but there is no proof yet, that actually the probability that you would do changes around a node with rank R should be exponentially decreasing with R. Okay. So this is what, I mean, in amortized fashion again, but so this is what we would like to have. Okay. And finally, yes, so adapting these algorithms to stratify the AVL trees, because you have variants of AVL trees. Let's say you have more constraints so that it will improve the upper bound you have on the height of your trees. And so, I mean, if they are constructed in a similar way, maybe you can hope to extend the tools that we have here, okay, from a weak variant of AVL trees to real AVL trees to the stronger variants of trees as well. Okay. Well, I think it's worth it because it's exactly the same kind of tools for designing the structure. So maybe the similar algorithm should work. Okay. And the main takeaway of the talk is that, well, I mean, okay, I'm in the AOFA community for a long time, but the last time I used probabilities, I mean, in the actual paper I wrote and not for trying to find the good objects, okay? So like I use it all the time for trying to find the good object, but then I just do worst case analysis, so the probabilities somehow vanish, okay? Well, so it has been a long time since I did that, but in general, I think what is a common part of the community that we like to analyze algorithms and data structures and processes about them. And in general, what I really like to do is to find something that is already used, okay, and to try to see, either I can prove that it's super efficient, or I can prove that it's not super efficient, it's efficient but not super so, and then we can improve it to be super efficient as well. Okay. So, well, I mean, this is nice. I mean, I think that it's what we may like to do together. Okay. next slide is like just the bibliographical resources, okay, that I used. So I did not mention any bibliographical element during the talk itself, okay. It's basically because like I have huge problems remembering the names of people, okay. But so I wanted to have a cheat code there, okay. So in particular, for instance, here you have those people who invented the different data structures like AVL trees or weight-bounded trees or red-black trees or weak AVL trees, okay. And then some other papers that may be relevant if you are interested at looking at the analysis of these data structures and the associated algorithms, okay. Well, thank you for your attention, and please ask questions that are not too difficult.